Hello, this is Zhenduo Wang and Qingyao Ai from the Information Retrieval Lab of the University of Utah. In this work, we propose to control the risk of conversational search via reinforcement learning. The reason why we are interested in this problem is that many recent studies have shown that asking clarifying questions is beneficial for conversational search. However, these existing studies often ignore one fact. That is, asking clarifying question has its own risks. For example, the question asked to the user can be totally irrelevant to user's information request, or maybe the user is asked too many clarifying questions before retrieved a real result. A common risk-unaware framework for conversational search is to first predict whether there is a need to ask clarifying questions, given the context. Then, based on the prediction, retrieve or generate a clarifying question if needed, and retrieve or generate a result for the user if a clarifying question is not needed. Then it is up to the user whether to reply to the clarifying question. If a relevant clarifying question is returned to the user, then the user will reply to the question. This gives the system more information in the context in the future to retrieve better results. If a bad clarifying question is asked to the user can choose to leave the conversation. Whenever a result is returned to the user, the conversation will complete. A notable problem in this framework is that the question retriever or generator can fail to retrieve or generate a good clarifying question, even when the need of asking a clarifying question is correctly identified. This will frustrate the user, giving them a hard time using our search system and may eventually drive user away from our search system. Our proposed risk control framework is different from the existing one in that it does not predict whether to ask a question or give an answer just by the request context. Instead, it does both a question and result retrieval or generation. And with the request context and these retrieved or generated results, a decision maker decides which action is better. We propose to balance the risks in asking a clarifying question and returning results to the user by doing this. We also build a system to instantiate our searching framework. In the system, we use the Parley encoder from Parley of Facebook as our retrieval models. We use it as re-ranker to re-rank the answer and clarifying question candidates given the request context. And we also experiment with their bi-encoder structure to test our framework with different retrieval models. In our experiment, we consider the answer re-ranking and clarifying question re-ranking as different tasks. So we use two sets of parameters for the answer re-ranker and question re-ranker. Both of them are first pre-trained on large Reddit corpora, and after that, the answer re-ranker is fine-tuned on answer re-ranking training samples and question re-ranker on question re-ranking training samples. For the decision maker, we use a simple feed-forward neural network. Its input consists of the user's initial query, the conversation context, the top K question and top K answer, and their re-ranking scores from the re-rankers. We use a BERT-based encoder to vectorize all the textual features and concatenate them with the score features for the neural net. This decision maker's goal is to evaluate the output from these re-rankers and decide which action is the better one. So this is essentially a classification task. To train such a classifier, we need to manually create training samples with labels that says whether a specific question or specific answer is better given a specific query and context. But creating such training samples will be very expensive, so we propose to use a reinforcement learning algorithm. Reinforcement learning algorithms are often based on state, action, and reward. In our algorithm, there are 3 different states and 2 actions. It all starts from the waiting state, where user is waiting for some response from the system. If the system decides to answer, it will transfer the waiting state into a finished state where the conversation will be complete. If the system decides to ask a question, then it can have 2 possible outcomes. If the question is good, then the user will reply to that question, and this information will be integrated into the next waiting state. If the question is bad, then user can leave the conversation. Then let's talk about the rewards. The reward for answering the query is always going to be the answering ranker's reciprocal rank score. This will naturally give good answers high reward and bad answers low reward. Then the reward for a good clarifying question will be very small. This number is usually far less than the reward for good answers, because we want to prevent the system from learning to accumulate this reward by asking clarifying questions endlessly. Then the reward for bad clarifying question will be a negative penalty because this is the worst scenario we want to avoid. So knowing there is a negative penalty, why would the system choose to ask clarifying question? The reason is that the system can reasonably hope to get a better answer from asking clarifying questions and having more information in a later waiting state. With the reinforcement learning algorithm, our decision maker is no longer a classifier that outputs a distribution of probabilities over asking question and giving answer. It now learns to predict the rewards of asking the specific clarifying questions and return the specific retrieved answers. We use Q-learning algorithm to define the target of decision maker output, and we optimize decision maker parameters using a square error loss. To test with our system, we propose to use a simulation experiment where our system will be interacting with a user simulator in multiple rounds until it shows results to the user or it fails on its way. We believe this will lead to better evaluation of our system compared to a single-turn next response selection task. Because in the simulation experiment, the behavior of a system is shown in a complete conversation, and it directly measures if a system can retrieve user some good results. The user simulator that will be interacting with our system is a simple looking up program. It checks whether it receives a response that is among the ground truth responses in the dataset. If the response is within ground truth and it has a follow-up, then the user will reply with it. Otherwise, if the response is not among ground truth, the user will assume that the system is talking about something irrelevant, and then the user will leave the conversation. To evaluate our system's performances on the simulation experiment, we propose to use 3 different metrics. The first one is recall 1, or it can be simply understood as the answer accuracy. It checks whether the returned result is the ground truth result in the dataset and returns a binary score accordingly. If the system causes user to leave the conversation, it will also receive a 0 on this metric. The second metric is the mean reciprocal rank of the final result. It is similar to recall 1, but also gives the system some partial score if it ranks the ground truth near the top but not the first. This will give some credit to the system if it avoids asking bad clarifying questions and causing user to leave, because it will then get 0. The last metric, decision error, is a bit unconventional. The decision error is the frequency of making worse decisions between asking a question and returning a result. There are 2 cases accounting for a worse decision. The first one is to ask a bad clarifying question, and the second one is to return a bad result when a good clarifying question is available. This metric is different from the previous 2 in that it evaluates on the intermediate system's decisions that are hidden from the final output. This will give us some insights of what is really happening behind these final results. Hence, we propose to use all of these 3 metrics to cover as many aspects of both the system and its results as possible. To compare to our framework, we include several baseline conversational search strategies. Q0A is a baseline that always returns an answer to the query without ever asking a clarifying question. Q1A is to always ask exactly one clarifying question and then always answer the query. Q2A always asks two clarifying questions before answering the query. The context prediction is the previously explained risk-unaware baseline, where the system first predicts whether to ask a question or answer the query based on context, and then return a question or an answer. The oracle model is a virtual strategy that can always choose the better action between asking a question and giving an answer. That is, it never makes decision error. The dataset we use in the experiments is the MS Dialog dataset, which contains of question-answering conversations from Microsoft Customer Help Forum. One good thing about this dataset is that it has a field indicating the final answer, so we can truncate the greetings and other noisy messages and focus only on the process of getting the answer. Now we are showing some experiment results on MS Dialog dataset. In our experiment, we test our system and the baselines with 3 different user models. A user model with 0 tolerance will immediately leave the conversation, seeing any bad clarifying question. A user model with 1 tolerance means it will tolerate the first bad clarifying question and leave on the second one, and so on. From the tables, we can see that our proposed framework performs better than all the baselines, excluding the oracle, on most experiments. Also, from both the polyencoder and biencoder experiments, we can see that our framework can improve the baseline strategies regardless of retrieval models we choose. Our decision maker has a long feature list, and especially there are both the textual features and ranking scores for the clarifying question and answer candidates. They seem to have some overlaps, and thus we conduct ablation studies on their effectiveness. We make 2 variations of our decision maker, which use the textual features and the score features individually. The table here shows the comparison of them in polyencoder experiments. From the table, we can see that in most cases it is the best to use both the textual features and the ranking scores, although it seems redundant. In the end, we want to summarize our contributions in this work. First, we propose a new risk-aware conversational search framework along with a system which can control the risk between returning a result to the user and asking a clarifying question. Second, we propose a reinforcement learning approach to train the proposed risk control system without annotated label for which action has lower risk during conversation. Last, we design a simulation experiment with different evaluation metrics which can evaluate whether a conversational search system can improve the answer quality and user experience in multi-turn conversations. Thank you.